trig identities. Now I feel like I have to like be fancier as I read things. Okay, so what we're introducing today is basically some equations or formulas that will be true regardless of whatever the angle is. Filling in the blank, we call these identities. So the idea is when we know true things about the different ratios like sine and cosine, you can write an equation and say this equation must be true. Because you can rearrange them and you can like substitute one equation into another equation, there's actually an infinite number of identities, but we're just going to look at some of the most common ones. And basically what we'll be doing through the unit is once we've introduced these formulas, you'll start with one expression and you'll try and use some of these formulas to say, okay, it's actually equal to this other expression. Before we kind of do that, what I'm going to do is build up a little, but can we just like refresh our angles? So let's make an angle. This can be theta. This will be x, y, and r. And let's just fill in some of the formulas that we know. Do you remember sine theta? Yeah. One of you has to yell it out loud and make me look good. What's the formula for sine theta? Yeah. Y over r. Cosine theta? X over r. Tan theta? Y over x. And then cosecant. R over y. Yeah. R over y. And I'm also going to write, this is also the reciprocal of sine, so I'm also going to write it as 1 over sine theta. Secant? Yeah, r over x. And it's also the reciprocal for cosine. And then cotangent? Yeah. And it's also the reciprocal for tan. So these statements for cosecant, secant, and cotangent are actually three of the identities that we've already been using. So an identity is just an equation or a statement that's true regardless of the angle. I am going to add in a couple extras for tan that we may or may not have looked at before. I honestly don't remember. But if we take, for example, our sine equation and we wanted to find a way to rewrite it for y, we could say that y is equal to r times sine theta. And we actually looked at a version of this. Do you remember with the unit circle where we made our r value 1 and we just said that y was equal to sine theta? So this is kind of like the extended version of that. Whatever r you have, this would be true. But also, if you just pick the unit circle, then it could just be y equals sine theta, which is a little bit easier. Same idea for cosine. If you wanted a statement for x, we can use this one here. And we can just multiply by r and say that x is equal to r cosine theta. And if we were on the unit circle and r was 1, it would just be y is cosine theta. These two are a little bit helpful because if we look at tan is y over x, right? This gives us kind of, I'm going to zoom in. This gives us another way of rewriting tan. If tan theta is y over x, it's also r sine theta divided by r cosine theta, using these two over here, right? And what's nice about this is even if you're not on the unit circle, what happens to your r values?
Cross out.
Yeah, so actually, I'm going to put this on the right. This gives us a new identity for tan, which is that tan theta is actually just equal to sine theta over cosine theta. And this is going to be one of the ones that we use a lot because sometimes when we have things like tan and cotan, what we actually like to do is rewrite it in terms of sine and cosine, and that allows us to sometimes like cancel things out and simplify. If this is tan, what would sort of a similar statement for cotangent be? Yeah, we would take the reciprocal, so it would be cosine theta over sine theta. So those are kind of going to be our starting pieces and building blocks. And the other kind of most common identity that we're going to use a lot is based off of the Pythagorean theorem. This one comes with a disclaimer that you don't need to be able to do this. I'm not going to ask you to recreate this identity on a test. So I'll maybe put a little disclaimer here. You don't need to derive this. Deriving is like creating or coming up with the formula yourself. So you won't need to create the formula. The formula will be on your formula sheet. But I find that it's kind of nice to show you where at least a couple of these come from, so you kind of get the idea of why it's always true. So for this first one, we're going to use the Pythagorean theorem, and we're going to use this same triangle. So we have legs of x and y, and we have a hypotenuse of r. How would you write a Pythagorean formula for that?
Squared plus y.
Yeah, so x squared plus y squared equals r squared. Now, if this is true, we can do some things to rearrange this formula. One of those things that I could do is, what if I divide the entire equation on both sides by r squared? So divide by r squared, divide by r squared, divide by r squared. Is that still going to be true? And as long as r is not 0, that should be true for all of our angles and x and y values, right? Now, if we think about this, another way you could write this, maybe I'll just do it to the right, is x over r squared. Oh, you got it. Y over r squared. And then the r squared over r squared is just going to be 1, so I'll just put in a 1. Yes, what is x over r equal to? Yeah, so this is actually cosine being squared. Do you remember the way we write cosine squared is like that, right? With the squared before the angle. And then what about the y over r? Yeah, so this one is actually sine squared. And if you add those two, it's equal to 1. And because we just did this with like a general x, y, and r, this should be true for any angle as long as your r isn't 0. And this is probably one of the most popular equations or formulas we use for trig identities. There's actually 2 more versions of this. So if we start with the same equation up here, the x squared plus y squared equals r squared, if you were to divide by x squared or divide by y squared, it actually gives you 2 more versions. I'm not going to do all 3 because you don't need to be able to recreate them. But if you, am I okay to scroll? If you flip onto the back side of the page at the top where it says Pythagorean identities, here's the first one that we just found. Why is it in the other order? I don't know. People like to put sine before cosine. It could be written the other way. If you write it cosine squared, it's still the same thing, right? And I don't know if that really looks useful or not, but the idea is if you have a really complicated statement and somewhere within that complicated statement, you're writing cosine squared theta plus sine squared theta, you can take those 2 terms and just say, hey, those 2 terms are equal to 1. And it's one way of making your statement a little bit easier. So the other 2 that you would come up with when you divide by x squared or when you divide by y squared, these are the other 2 Pythagorean identities. They come from the same equation, but we're not going to derive all 3. We're basically just going to say that all 3 of them are true. If you want to check one, you can check one, try it yourself, and be surprised that it's true. But basically, we're going to take it for granted that all 3 of these are true. Sound okay? So what we're going to do today is we're going to kind of focus on the top identities. So the Pythagorean identities are kind of the new ones we're introducing. We already know our reciprocal identities. Now we also know our extra identities for tan and cotan. The other thing I like to point out is what's called a corollary identity. The idea is basically you can rearrange the equation. So if this equation is true, sine squared plus cosine squared is equal to 1, what if somewhere in there you actually have something like 1 minus cosine squared? So let's say you see this expression. What would that be equal to? Yeah. So the idea is you can rearrange this formula or rearrange this equation in kind of different versions and it will still be true. And the same thing if you had 1 minus sine squared theta, what would that one be equal to? Cosine squared theta. So the idea is that you can rearrange these. You do need to be a little bit careful that when you rearrange, it's still a true statement. Like if you saw 1 plus cosine squared theta, there isn't a way that you can rearrange this to have 1 plus cosine squared theta, but you could move the cosine to the other side and have 1 minus cosine squared theta, right? So just keep an eye out when you see these terms. Like if you see a 1 and you see a sine squared theta, keep an eye out, does it actually end up in this form 1 minus sine squared theta? Then you could replace it with a cosine if you needed to write things in terms of cosine. Does that kind of feel okay? Okay, I won't rearrange all of them, but the idea is the same, that for these identities that are true, you can move terms from one side to the other side to have it kind of in a different format and still get an equation that's true that you can use if you need to. The other thing we're going to do today is we're going to look at basically just simplifying. So if you get a more complicated statement, is there a way to do whatever operations are there and maybe write it with less trig functions or write it with just a number instead of a trig function? Before we kind of get into the complicated ones, what I'm going to do is just show you some techniques that can be used for simplifying. So am I okay to slide? This is kind of like our main content. I'm going to show you the 4 techniques just like in isolation, and then we'll look at some examples and decide what technique would be helpful. So our first technique is if you have 2 different things, if you don't know what your angle is, you don't really have a good way of adding those, but something you could do is you could write it with a common denominator. So this is a fraction with a denominator of cosine theta. Is there a way we could rewrite this first expression to also be something with a denominator of cosine theta? What could we do? Yeah, and if we want to multiply and we don't want to change its value, we can't just say, oh, let me multiply by cosine. But what could you multiply by? Cosine over cosine, right? Multiply by 1, yeah. So if you multiply by cosine theta over cosine theta, are you changing its value? No. But it's giving you a way to rewrite an equivalent fraction. That way you have a common denominator. So I would write this as cosine squared theta over cosine theta, plus our second fraction is sine theta over cosine theta. And the nice thing about writing with a common denominator is it now allows us to rewrite as a single fraction, because for adding fractions, you want the same denominator, then you can add the numerators, right? So I could also write this as cosine squared theta plus sine theta all over cosine theta. Now, on its own, that one maybe doesn't look any simpler. Imagine if we had had a sine squared theta there. This would have been so much nicer, because as soon as we had a sine squared theta there, we could say the entire top part was just 1. In this case, it might not look simpler, but it's a little bit simpler in that we only have one fraction or term and that we've done the operation that was there. Usually this would be like one step of a multi-step process where we're trying to make one equation look like another equation. So this is one of the techniques we use, is when you need to add 2 things, write them with a common denominator first. Feel okay? Yeah. All right, next technique is factoring. This says factor as a difference of squares, but honestly, any kind of factoring can be very helpful. If it's a little bit easier, like if you have a trig function and that feels awkward to factor, you could also substitute in another letter temporarily. Like if you thought of this as 1 minus a squared, that would factor into 1 minus a and 1 plus a, right? You can factor with the trig function the same way. So you can factor this into 1 minus cosine theta times 1 plus cosine theta. Okay. On its own, this doesn't necessarily look simpler, but where I would do this is imagine if you had a fraction with this in your numerator and you had a 1 minus cosine theta in your denominator. Sometimes factoring your numerator and your denominator will let you divide out things that are in both, and that's another way of simplifying. Same thing if you have 2 terms for a difference of squares. This could be like a plus b times a minus b. That's a squared minus b squared, right? So if I did that with this, this would be secant theta plus tan theta times secant theta minus tan theta. So on its own, they're equivalent. It doesn't really look any simpler, but the idea is if you were trying to do something where you had something in factored form, also factoring this could help. Or if you have a numerator and a denominator and they both do factor, sometimes they'll have a factor in common that divides out. Feel okay? Okay. Third technique. Change everything to sine and cosine. Basically, this means anywhere you see a tan or a cotan, can you instead write it in terms of sine and cosine? The way I would do this one, I would write like, I would maybe rewrite the division or just write it as a multiplication problem. But let's rewrite as division first. So this is tan theta divided by secant theta, right? But I have a way of writing tan theta in terms of sine and cosine. I also have a way of writing secant theta as cosine instead if I take a reciprocal, right? So if I wanted to rewrite this, what is tan theta equal to if you check your formula sheet? Sine over cosine. So this is sine theta over cosine theta. And then it's going to be divided by, what is secant theta equal to? 1 over cosine theta. Yeah, oh. So if you then rewrite this as multiplication, sine theta over cosine theta times cosine theta over 1. Yeah, what's going to divide out of the numerator and denominator? One of the cosines. And what are we left with? This is probably an actually really good example of simplifying, because instead of having 2 trig functions, we end up with just 1. So when we talk about trig identities, because I know the unit is called trig identities, when you make a statement and you say something like tan theta over secant theta is equal to sine theta, when you say this, that's a trig identity. It's a formula that will always be true, presuming you're not dividing by 0. We'll talk a little bit about restrictions at the end too, which is basically just look at the denominator and say that it can't be 0. But the idea is that as long as your denominator isn't 0, this equation will always be true. That's what we called it, trig identity. Feel okay? Okay, last technique. Am I okay to slide?
Yes.
All right, last technique is multiplying by the conjugate. This one kind of has like limited use, but the idea is if you have something like with 2 terms and it doesn't factor and you don't have any other factors, something you can do is if you multiply by the conjugate and kind of create a difference of squares, that difference of squares might actually match a Pythagorean identity. Do you remember what a conjugate is as I talk about conjugates? So like if we had something like 1 minus sine theta, do you remember what the conjugate is? Yeah, it's going to be the same 2 terms, but with the opposite sign in between. So 1 plus sine theta. They're not equal, but they're conjugate. So when you multiply these 2 together, the idea is you create a difference of squares, right? Like, do you remember how we said a minus b times a plus b is equal to a squared minus b squared? We're basically creating a difference of squares, and the nice thing about difference of squares is if you end up with something that matches a Pythagorean identity, then it's going to simplify further. Now we do have to be a little bit careful because we don't want to change the value. So you can't just randomly multiply by 1 sine theta, but what can you multiply by? Jaden, that was your cue. What can you multiply by?
Me?
Yeah, you yelled 1 last time.
I feel pressure because I'm on video.
It was 1 again, I'm sorry.
Oh, whatever.
Wait, should I be using code names for everyone?
Oh, but then 1 can equal to the thing plus anyway.
No, that's okay.
Multiply by 1, multiply by 1.
Famous on math week.
Okay, good. For like the 4 viewers. So someday, like 80 years from now, if YouTube is still a thing. So multiply by 1, basically you can multiply by anything as long as it's the same in the numerator and the denominator, because then you're not changing the overall value. So if you want to multiply by the conjugate, multiply by 1 plus sine theta over 1 plus sine theta. And if it helps, you don't really need the brackets, but if it helps you kind of imagine if you wrap it in brackets like that, just so you remember to multiply thoroughly, you can do that. What would happen to our numerator if we do this? It's just going to be 1 plus sine theta, right? What would happen to our denominator if we did this? It's a difference of squares, so it's going to be a squared minus b squared. In our case, it's going to be 1 squared, which is 1, minus sine squared theta. Where would this maybe be useful? Yeah, we have an identity that says what 1 minus sine squared theta is equal to. So if you had, for example, a cosine squared theta or even a cosine theta in the numerator, if you needed to rewrite in terms of cosine, it would be really helpful to do that. So on its own, this didn't really do a lot, but it did rearrange it. But if we're using it to simplify, this is kind of one of the techniques that helps sometimes. Because imagine you had a cosine in the numerator, being able to write the denominator in terms of cosine would be helpful. This is sort of like I don't pick this technique very often, but when I see a denominator, or sometimes a numerator, but it's 2 terms and one of those terms is 0, no, one of those terms is 1 and the other one is a trig function, That's usually when I try to multiply by a conjugate, because you'll get something squared and it might be one of the Pythagorean identities. Okay, let's do a little bit of the examples. I don't think I want to do every single example, but we'll pick some of them, and then we'll maybe do a few more next class. Can we flip the page? Yeah. All right, so let's start with example 2. Example 2, we have two separate things. We need to do some subtraction. What do you need in order to be able to subtract these two things? Common denominator, because they're fractions. So I would probably go with common denominator. One of my denominators is sine squared theta, so I should make the other one also sine squared theta. So rewriting this, first term can stay the same, 1 over sine squared theta. How can I rewrite the 1 so that the denominator is sine squared theta?
Sine squared theta over sine.
Yeah, anything over itself is going to be 1, so sine squared theta over sine squared theta. Okay. Then at this point, once I have a common denominator, I can sort of write them in one fraction where I add or subtract the numerators. So my numerator would be 1 minus sine squared theta over sine squared theta. When we get to this point, are we allowed to cross anything out? Is there anything we can divide out? Because our numerator is not factored, and you can't just cross out the sign because that 1 does not have a sign that can be divided out. So you do have to be a little bit careful there that you're not doing any illegal math. But is there anything that 1 minus sine squared theta is equal to? Yeah, so we could say, if we use that identity, we could rewrite the numerator as cosine squared theta, and then our denominator is sine squared theta. And again, we don't really have anything that we can divide out or cross out, but is there anything you notice about this cosine over sine? Yes?
Cotangent squared?
Yeah. So as a little reminder, it's on the formula sheet, but cotangent is equal to cosine over sine. That would still be true when squared, right? So this is equal to cotangent squared.
That is amazing.
Later on, like what we'll be doing next week is you could possibly be given this left side and you could be given the right side. And the idea behind proving an identity is we would say, here's the left side, here's the right side of the equation, prove that they are equal to each other. And the idea would be if you start with the left side and you rearrange it without changing its value, but you just write equivalent statements until you get to the right side, then you can say, well, clearly they're true because we were able to rearrange the left side until it equaled the right side. So right now we're just going to start with one side and we're going to try and simplify as much as we can. What's going to happen next week is you'll be given the answer, kind of, if we consider this an answer, but you'll be showing the steps in the middle to show why is one side equal to the other side. Feel okay? Kinda? Okay, let's do one on the next line. I just want to get a variety of them and then we can come back and do some of the extra examples on Monday if we want to. So let's go example 3. We might do both 3 and 4 because they're sort of different techniques. Okay, I only have one fraction, so I'm not really worried about a common denominator. I have a lot of terms. There's a cosecant, there's a cosine, there's a cotangent.
That's scary.
There's kind of two things I would consider. I would consider, can I write in terms of sine and cosine, or I would consider conjugate just because I have a binomial. But if I look at the cosine and the cotangent, I don't think I have one trig identity that has both of those, do I? Like a cosine squared minus cotangent squared, I don't think I have one of those. So it wouldn't really be helpful to multiply by the conjugate. You could try it, but it probably wouldn't make it any simpler. So this is where I would maybe try writing in terms of sine and cosine, and I'm just going to do a mega fraction because we're going to have a fraction in the numerator, we're going to have a fraction in the denominator. So I'm going to maybe make like a big fraction with little fractions in it. So I will try and give myself a little extra space. So for our numerator, I'll just leave the 1 temporarily, but is there a way to write cosecant in terms of sine and cosine?
Like,
What is cosecant equal to? Cosecant is 1 over sine, so I'm just going to kind of do like a small fraction inside my larger fraction. So for each one of the trig identities, I'm basically trying to write it in terms of sine, cosine, or both. Cosine is already in terms of cosine, so I'll leave that. But is there a way I can rewrite the cotangent?
Cosine.
Cosine over sine? Do you notice anything kind of interesting about this?
Yes.
What do you notice?
I don't know.
They're both oversized.
Get the sign.
Yeah, look at that. They both have something in front and then a fraction over sign. There's a couple of ways you can deal with this. What I actually kind of notice is, do you notice how in the denominator, both of these terms have a cosine? What if we tried factoring out the cosine? So I'm going to leave the top part the same, and I'm still going to, I'm going to stick with the awkwardly large fraction just for now. But our numerator is 1 plus 1 over sine theta. In our denominator, if I factor out a cosine theta, what's going to be left? If I factor out a cosine theta, what's left there?
1
1?
plus 1 over sine.
Oh, look at that. 1 over sine. So if I factor cosine from both of those, what do we have? We have like this whole lovely binomial that's in the numerator and the exact same thing as in the denominator. What could we do with that? Yeah, divide out that entire binomial. If it's in the numerator and the denominator, you can divide it out of both. So what would this then be equal to? This just becomes a 1, this becomes a 1. We have 1 over cosine theta. Or if you don't want to have the fraction, you could write that as secant theta. I would probably take either. But we went from this lovely complicated fraction into a super complicated fraction that factors so nicely. This is clearly more simple than that, right? I think example 5 factors similarly, so I'll skip example 5. Let's do 4 because I think 4 is kind of a factoring example, and then I think we'll skip ahead to the restrictions for now and save the rest for Monday. Yeah?
Okay.
Okay. Just because you're all like falling asleep on each other right now. You know. All right. We have cosine to the power of 4. We have cosine squared. We have a 1. We have 3 terms. There's nothing we can directly factor out of all 3 terms, but I do notice that I have a trinomial. It might almost be easier to see how you can factor it if you do a little bit of substitution. Like if you said, let A equal cosine x, then rewrite this as A to the power of 4 minus 2A squared plus 1. Does that make it a little bit easier to see how you can factor it?
Yes.
Maybe. So this one is not a difference of squares because it has 3 terms, but I could still factor it. If my first term is A to the power of 4, what's my first term in the binomials? It's probably going to be like A squared times A squared, right? My last term is 1, so what are the 2 numbers that I'm multiplying? What 2 numbers multiply to 1? It must be 1, 1, or it could be negative 1, negative 1. Do you notice this middle term has a negative? So it must be A squared minus 1 times A squared minus 1. And now that we've factored that so nicely, you could have factored it directly with the cosine if you didn't do the substitution. I find it a little bit easier to see how to factor it if you substitute. But once you factor it, you can just put the cosine back in there. So this is cosine squared x minus 1 times cosine squared x minus 1. I realize now that I could have written 1 bracket and then wrote squared, and I didn't, but that's okay. I guess I'm committed to this.
So it's sine.
It's close. We know that, let's put it on the side. We know that sine squared x plus cosine squared x is equal to 1.
Right.
If we had cosine squared x minus 1, that means we must move the 1 to the left side. What is that going to be equal to?
Sine.
Negative sign, because when you move it to the right side of the equation, it's negative sine squared x. So think about it as moving the 1 to the left. Think about it as moving the sign to the right. So cosine squared minus 1 can actually be replaced with negative sine squared x. And same is true for the second one since it's exactly the same. And in this case, if you miss the negative, you would almost actually get away with it because we're doing a negative times a negative and it's going to become positive anyways. How could I simplify these further? Just do the multiplication. So negative times negative is positive. Sine squared times sine squared is going to be sine to the power of 4x. Shall we skip ahead to the restrictions on the next page, and then we'll come back and do like an example with conjugate next class? All right, restrictions. Fancy disclaimer, just like any algebraic expression, a trigonometric expression cannot have 0 in the denominator. If you look at something like this, there are no obvious denominators, but if you start to think about what do these things equal, like what is tan x actually equal to?
Tan x?
Yeah, what is tan equal to?
Sine
Sine over cosine. Over cosine, there's a cosine in the denominator. So even though tan itself might not remind you that there's a restriction, as soon as you think about having something in the denominator, there's a restriction. Or you might happen to look at tan and be like, oh yeah, I love the tan graph so much. I remember there's an asymptote. Asymptote is restriction, right? Something that x is not allowed to be equal to. If you don't remember the asymptote, it's maybe easier to realize that there's a cosine in the denominator. So let's just take this example. This one is tan x minus cosecant x. And let's see if we can rewrite this as some fractions so we can see what's actually in the denominator. So tan x is actually sine x over cosine x. Yeah, this one for cosecant, it's 1 over sine x. And it doesn't ask me to simplify or do anything like that, although this is pretty much as simplified as we would get, but it does say consider the restrictions. So think about anything you have in the denominator. What is not allowed to be equal to 0?
cosine.
Yeah. So we get some restrictions from cosine x is not allowed to be equal to 0. What else is true? Sine x is also not allowed to be equal to 0. And this is where you're going to have to remember your special angles a little bit. So let's just draw in some points that would be on the unit circle. So if cosine x was equal to 0, just so we can find those angles, that happens up here and down here, that your x value is 0, right? Or sorry, this is horrible. I should have used theta, not, I'm going to use something different. I don't know. A bad choice of x versus x, but your angle happens up here and down here. That's where cosine of the angle would be 0, right? What angles is that?
9.
Pi over 2 and 3 pi over 2. So I'm going to say that x cannot be equal to pi over 2 or 3 pi over 2. Because those are the places that would make cosine x equal to 0. That would mean we were dividing by 0. So cosine x is not allowed to be 0, so these are the angles that are not allowed to go into that identity because you would be dividing by 0. If we do something similar for sine, what angles make sine x equal to 0? It happens here and it happens here. Yeah, 0 and pi. So x is not allowed to be 0 and x is not allowed to be pi. Double checking our domain, it's from 0 to 2 pi, but we're not including 2 pi, so just the 4 angles. So the idea is if it would make the denominator 0, it's not allowed. So what we can do is try setting the denominator equal to 0 and find those angles. Those are the angles that are restricted or not allowed. If you want to put all your restrictions together, in order, we could go 0, pi over 2, pi, 3 pi over 2. That's pretty much it for a restriction. Restrictions are not too bad. They're okay, right? All right, and that's where we're going to cut it off for today.